Welcome to our walkthrough of the problem Lonely Pixel I. In this session, we'll explore the challenge, break it down step by step, and outline an effective solution. Let's dive in and get started. This problem, called Lonely Pixel I, involves analyzing a binary grid image represented as a 2D character array called picture. In this grid, each element is either B, representing a black pixel, or W, representing a white pixel. The goal is to determine how many black pixels in the grid are considered lonely. A black pixel is considered lonely if it satisfies two conditions. First, there are no other black pixels in the same row, and second, there are no other black pixels in the same column. The input to the problem is this 2D array, where m is the number of rows and n is the number of columns. The output is an integer representing the total count of these lonely black pixels. To understand how the problem works, let's look at an example. Here, we have a grid where W represents white pixels and B represents black pixels. The input grid is a 3x3 matrix. The task is to identify the black pixels that are lonely. For example, the black pixel at position 0, 2, which is in row 0 and column 2, has no other black pixels in either its row or column. Therefore, it qualifies as a lonely pixel. We'll continue analyzing the rest of the grid to complete the count. Looking further into the same example, the black pixel at position 1, 1, found in row 1 and column 1 also satisfies the conditions of being lonely because it is the only black pixel in its row and its column. Similarly, the black pixel at position 2, 0, in row 2 and column 0 has no other black pixels in its row or column, making it lonely as well. Adding these up, we find that the total count of lonely black pixels in this grid is 3. Now, consider a second example where the grid is filled entirely with black pixels. In this second example, the input grid is a 3x3 matrix where every cell contains a black pixel. Because each row and column contains multiple black pixels, none of the pixels can be considered lonely. A lonely pixel, by definition, must be the only black pixel in both its row and column. Since no pixel in this grid satisfies that condition, the total count of lonely pixels here is 0. Let's examine a third and final example to see another variation. In the third example, the grid is a 2x2 matrix. The black pixel at position 0, 0, in row 0 and column 0 has no other black pixels in its row or column, making it a lonely pixel. Similarly, the black pixel at position 1, 1, in row 1 and column 1 also satisfies the condition of being lonely. This gives us a total count of 2 lonely pixels. Additionally, the constraints for this problem specify that the grid can have dimensions up to 500 by 500 and that each cell must be either B or W. Wedge cases include single-cell grids and scenarios where there are no black pixels at all, which would result in an output of 0. Sparse grids with large dimensions may also require optimized solutions for performance. When considering how to approach this problem, the brute force method is the most intuitive starting point. Here, for every black pixel in the grid, we would scan the entire row and column to check if it is lonely, that is, if there are no other black pixels in the same row or column. However, this approach is highly inefficient because each check involves scanning rows and columns repeatedly. For a grid with dimensions m by n, this results in a time complexity of O, m*n*, m plus n, which becomes impractical as the grid size grows. To optimize, we can leverage a key observation. Instead of repeatedly scanning rows and columns for each black pixel, we can count the number of black pixels in each row and column just once and store these counts in auxiliary arrays. By doing so, we can determine whether a black pixel is lonely in constant time. The optimized steps involve two main traversals of the grid. First, we populate the row_counts array with the number of black pixels in each row and the col_counts array with the number of black pixels in each column. Then, during the second traversal, we check for each black pixel whether its row and column counts are equal to 1, which would indicate that it's a lonely pixel. This drastically reduces the time complexity to O, m*n, making it much more efficient for larger grids. There's also an alternative optimization that uses hash maps to count black pixels in rows and columns. This method operates similarly to the array-based optimized solution but replaces the auxiliary arrays with hash maps. Hash maps can be particularly useful in scenarios where the rows or columns are not contiguous or are labeled in a non-numerical way. For example, if the grid rows and columns had custom identifiers instead of sequential numbers, hash maps would provide the flexibility to handle such cases. However, this comes at the cost of additional overhead. Hash map operations, while still efficient, are generally slower than array indexing due to the need for hashing and potential collisions. In this problem, where the grid structure is regular and rows and columns are sequentially indexed, the added flexibility of hash maps doesn't provide enough benefit to outweigh the performance overhead. As a result, we chose the array-based optimized approach for its simplicity and efficiency. While the brute force method has a straightforward implementation, its time complexity renders it unsuitable for larger grids, and the hash map-based optimization introduces unnecessary complexity in this particular context. Each approach comes with its own trade-offs. The brute force method is straightforward and easy to understand, but it's prohibitively expensive in terms of computation, with a time complexity of m*n*m plus n. On the other hand, the optimized approach, which uses auxiliary arrays to count black pixels row-wise and column-wise, significantly reduces the complexity to m*n*. This makes it highly efficient and well-suited for structured grid inputs like the one in this problem. The hash map-based optimization offers more flexibility, especially for grids with non-contiguous or non-numeric row and column labels. However, this flexibility comes at the cost of slower operations compared to arrays, which is unnecessary for this problem given its structured grid format. Ultimately, the optimized approach using arrays strikes the best balance between simplicity, efficiency, and scalability. It avoids redundant computations and provides a clear, effective solution with minimal trade-offs, making it the ideal choice for solving this problem. The problem we're tackling involves a grid of pixels, represented as a 2D character array, where each pixel is either B4 black or W4 white. Our goal is to identify all lonely black pixels. A black pixel is lonely if it is the only black pixel in both its row and its column. To solve this, we start with a straightforward brute force approach. First, we need to validate the input. If the grid is empty or null, we return 0 immediately to avoid unnecessary computation. Next, we initialize some essential variables. The dimensions of the grid are stored as M4 rows and N4 columns, and we set up a counter, lonely_count, starting at 0. This counter will keep track of the number of lonely black pixels we find as we process the grid. Now, we move on to the core of the brute force algorithm. We iterate through every cell in the grid using nested loops. The outer loop goes through each row, while the inner loop goes through each column. For every cell at position i, j, we check if it contains a black pixel, represented by B. If it does, we then verify two critical conditions for it to be considered lonely. First, we scan the entire row I to make sure there are no other black pixels in that row except at the current position i, j. Then, we check the entire column j to ensure the same condition holds true there as well. If both conditions are met, it means the pixel at i, j is lonely, so we increment the lonely_count by 1. Finally, after traversing the entire grid, we return the value of lonely_count, which gives us the total number of lonely black pixels. To better understand this brute force approach, let's break it down with some key insights. A black pixel is considered lonely only if it's the sole B in both its row and column. This means that for every black pixel we encounter, we need to perform two additional scans, one for its row and one for its column. While straightforward, this results in a time complexity of m*n*m plus n, because for each cell in the grid, we may need to check all rows and columns. There are also important edge cases to consider. For example, a grid with no black pixels should return 0, while a grid where every pixel is black would return 0 as well since no pixel would be lonely. Additionally, grids with only one row, one column, or irregular dimensions may require extra care to ensure correctness. Lastly, the grid itself is represented as a 2D array of characters, and we use a simple integer variable, lonely_count, to track the result. We can significantly optimize the brute force approach by leveraging pre-computed counts of black pixels in each row and column. Instead of scanning rows and columns repeatedly, we can pre-process the grid in a single pass. To do this, we create two arrays, row_count and col_count. These arrays are initialized to 0 and will store the count of black pixels for each row and column, respectively. As we traverse the grid, we populate these arrays by incrementing row_count, I, for every black pixel in row I and col_count, j, for every black pixel in column j. Once these counts are prepared, determining whether a black pixel is lonely becomes a simple lookup operation in the arrays. If both row_count, I, and col_count, j, equal 1 for a given black pixel, it is lonely. This optimization reduces the time complexity to O(m*n), making it far more efficient for larger grids while still yielding the correct result. This solution tackles the problem of finding lonely black pixels, B, in a 2D grid, where a B is lonely if it is the only black pixel in both its row and column. Let's break down the solution step by step. First, the function begins by validating the input. If the grid is empty or contains no rows, it immediately returns 0, as there are no pixels to evaluate. Next, it initializes two arrays, row_counts and col_counts. These arrays will store the count of black pixels in each row and column, respectively. The dimensions of these arrays are determined by the number of rows and columns in the grid. The first major step is to iterate through the entire grid. For each cell, if it contains a black pixel, B, the corresponding row and column counters are increment. This pre-processing step ensures that we efficiently count the number of black pixels present in each row and column. The second step is to iterate through the grid again, this time identifying lonely pixels. A pixel is lonely if it is black, B, and the count of black pixels in both its row and column is exactly 1. For each such pixel, the lonely_count variable is increment. Finally, the function returns the total count of lonely pixels. The algorithm is efficient, as it processes the grid twice, resulting in a time complexity of O(n*m), where n is the number of rows and m is the number of columns. This ensures the solution is scalable for larger grids. Key edge cases handled by this implementation include grids with no black pixels, grids with only one row or column, and grids where all pixels are black. The use of auxiliary arrays for row and column counts ensures clarity and efficiency throughout the solution. Here, we start by defining the findLonelyPixel method, which takes a 2D character array picture as input. The first step is to handle edge cases, such as if the picture array is null, empty, or has no columns. In these cases, we simply return 0 since there are no pixels to process. Next, we determine the dimensions of the picture, storing the number of rows and columns in rows and cols, respectively. We then set up two arrays, rowCounts and col_counts, to keep track of how many black pixels, represented as B, appear in each row and column. These arrays will help us efficiently determine if a pixel is lonely. After initializing the arrays, we loop through every cell in the picture. For each black pixel we encounter, we increment the corresponding row and column counts. This ensures that by the end of the loop, we know exactly how many black pixels exist in each row and column of the picture. Now, with the row and column counts calculated, we proceed to identify the lonely pixels. A pixel is considered lonely if it is a black pixel, and there is exactly one black pixel in both its row and its column. To check this, we iterate through the picture again. For each black pixel, we verify that the corresponding values in rowCounts and col_counts are both equal to 1. If they are, we increment the lonelyCount variable, which tracks the total number of lonely pixels. Once all cells have been processed, we return the value of lonelyCount as the final result. This completes the implementation of the solution, which efficiently counts lonely pixels by leveraging the pre-computed row and column counts to avoid redundant checks. We begin with a 3x3 grid where W represents white pixels and B represents black pixels. The goal is to determine how many lonely black pixels exist. A lonely pixel is defined as a black pixel that is the only one in its row and column. First, we initialize some variables. Rows and cols store the grid dimensions, both set to 3 here. We also create two arrays, row_counts and col_counts, initialized to zeros, to track the number of black pixels in each row and column. Next, we iterate through the grid to count the Bs in each row and column. Starting with the first row at I equals 0, we examine each column. At j equals 0, the pixel is W, so no changes are made. At j equals 1, we find a B, so we increment row_counts, 0, and col_counts, 1, by 1. At j equals 2, the pixel is again W, so no change occurs. This process continues for the remaining rows, as we'll see shortly. In the second row, I equals 1, we again examine each column. At j equals 0, the pixel is W, so no changes are made. At j equals 1, we find another B, so we increment row underscore counts, 1, and col underscore counts, 1. This updates the counts to row underscore counts equals 1, 1, 0, and col underscore counts equals 0, 2, 0. At j equals 2, the pixel is W, so no change occurs. Moving to the third row, I equals 2, we again iterate through the columns. At j equals 0 and j equals 1, both pixels are W, so no changes are made. At j equals 2, we find a B, so we increment row underscore counts, 2, and col underscore counts, 2. This gives us final counts of row underscore counts equals 1, 1, 1, and col underscore counts equals 0, 2, 1. With the counts established, we proceed to identify lonely pixels. Starting with the first row, at j equals 1, we find a B, but it's not lonely because col underscore counts, 1, is greater than 1. Similarly, no lonely pixels are found in the second row. In the third row, we examine the pixel at j equals 2, which is a B. This time, it qualifies as lonely because both row underscore counts, 2, and col underscore counts, 2, are equal to 1, meaning it's the only black pixel in its row and column. We increment the lonely underscore count to 1. With all rows and columns examined, the final output for this example is 1, indicating there is one lonely pixel. Now let's consider another example, where the grid contains no lonely pixels. In this case, the grid is a 2x2 matrix entirely filled with black pixels. We start by initializing rows, cols, row underscore counts, and col underscore counts. The row and column counts are both arrays of size 2, initialized to zeros. Next, we count the number of B's in each row and column. For the first row, I equals 0, we increment the counts for both columns. After processing this row underscore counts becomes 2, 0, and col underscore counts becomes 1, 1. For the second row, I equals 1, we do the same, incrementing the counts for both columns again. This updates row underscore counts to 2, 2, and col underscore counts to 2, 2. Now, we check for lonely pixels. Since every B has row and column counts greater than 1, none of them qualify as lonely. The lonely underscore count remains 0. Therefore, the output for this example is 0, meaning there are no lonely pixels. Finally, let's explore a third example where multiple lonely pixels exist. In this case, the grid is a 3x3 matrix with black pixels in a diagonal arrangement. We initialize rows, cols, row underscore counts, and col underscore counts as before. As we iterate through the grid to count the B's, we find one black pixel in each row and column. This results in row underscore counts equals 1, 1, 1, and col underscore counts equals 1, 1, 1. Next, we check for lonely pixels. Since each B has row and column counts of exactly 1, all 3 black pixels are lonely. We increment the lonely underscore count for each, resulting in a final count of 3. Thus, the output for this example is 3, indicating there are 3 lonely pixels. This demonstrates how the algorithm efficiently handles grids with varying configurations of B's. The time complexity of the solution can be broken down into 2 main steps. First, the algorithm iterates through the matrix to count the number of B's in each row and column. This involves 2 nested loops, one for traversing the rows and another for the columns, resulting in a time complexity of O, m*n, where m is the number of rows and n is the number of columns. Next, the algorithm performs another pass over the matrix, this time checking if each B is a lonely pixel. The condition for being lonely is that the row count and the column count for that specific pixel must both equal 1. Again, this step involves iterating through all rows and columns, contributing an additional O, m*n, operations. Both steps are sequential, so their time complexities add up, but each is proportional to the size of the matrix. Combining the 2 steps, we find that the overall time complexity is O, m*n, plus O, m*n, which simplifies to O, m*n. This remains consistent regardless of the input, as the algorithm must traverse the entire matrix in both steps. Even in the best-case scenario, such as when there are no B's or when early termination might seem possible, the algorithm still processes every element in the matrix, so the best case complexity is also O, m*n. Similarly, in the worst case, where the matrix is fully populated with Bs, the time complexity remains linear with respect to the size of the input. Turning to space complexity, the algorithm uses two auxiliary lists, row_counts to store the number of Bs in each row and col_counts to store the number of Bs in each column. These lists require O, m, and O, n space, respectively. Additional variables such as counters use constant space, O1, and do not scale with the input size. When we compare this solution to a naive approach, the efficiency becomes even clearer. A brute force method would involve checking each potential pair of Bs to determine if a pixel is lonely, leading to O, open parenthesis m times n close parenthesis squared, operations in the worst case, especially when the matrix is densely populated with Bs. In contrast, the provided solution avoids redundant checks by first pre-processing the row and column counts in O, m*n time, followed by a single additional pass for the loneliness check. This pre-processing step ensures that we only process each matrix element twice, optimizing the algorithm for both time and space. The use of auxiliary space, O, m+n, is a deliberate trade-off, as attempting to reduce space further would likely result in higher time complexity. Thus, the solution strikes an effective balance between computational efficiency and memory usage. To mathematically validate the big O notation, consider that for a matrix of size mxn, each element is processed exactly twice, once during the counting step and once during the loneliness check. This means the total number of operations is directly proportional to the size of the matrix, confirming the time complexity is O, m*n. For auxiliary space, the algorithm uses O, m, for the row counts and O, n, for the column counts, resulting in O, m+n, space complexity. These additional structures allow the algorithm to efficiently store intermediate results without needing to revisit matrix elements repeatedly. In conclusion, the algorithm achieves the best possible performance for this problem, with linear time complexity relative to the input size and minimal additional space usage, making it both optimal and scalable for large matrices. When solving grid-based problems like lonely pixeli, there are some common mistakes to watch out for. First, relying on brute force methods can be problematic because they often lead to inefficient solutions with time complexities of O, n cubed, or worse. Instead, it's important to consider optimizations such as pre-computing row or column counts, or using hash maps to track the distribution of black pixels. Another frequent issue is misunderstanding the problem statement, particularly what it means for a black pixel to be lonely. Remember, a black pixel is only considered lonely if it is the sole black pixel in both its row and its column. Forgetting this condition can lead to incorrect results. Additionally, edge cases like empty grids, grids with only one row or column, or those with no black pixels at all can easily be overlooked, causing runtime errors or incorrect outputs. Lastly, some solutions make the assumption that grids are always square, which is not guaranteed. This can result in index out-of-range errors when working with rectangular grids. It's crucial to keep these pitfalls in mind during implementation. Overcomplicating the implementation is another trap to avoid. Overusing nested loops or adding redundant checks not only increases the complexity of your code but also makes it harder to debug and less efficient. Instead, focus on simplifying your approach while maintaining clarity. For grid problems, a helpful strategy is to recognize recurring patterns. Many of these problems involve counting or validating rows and columns, so pre-processing data like row or column counts can minimize redundant computations. Balancing time and space trade-offs is also essential. For instance, pre-computing row and column counts might use additional space, but it can significantly improve runtime performance. Testing your solution with edge cases, such as grids with no black pixels or those with multiple black pixels in a single row or column, is critical to ensure correctness. During interviews, articulate your thought process clearly. Explain your approach, discuss trade-offs, and outline your plan before diving into the code. This demonstrates structured thinking and helps avoid unnecessary rework. The concepts in lonely pixeli are closely related to several other grid-based problems, which can help you strengthen your problem-solving skills. For example, LeetCode 73, Set Matrix Zeros, involves marking rows and columns for efficient processing, a technique similar to pre-computing counts. LeetCode 36, Valid Sudoku, requires validating rows, columns, and subgrids, which aligns with the row and column checks in this problem. LeetCode 200, Number of Islands, focuses on marking and traversing connected components in a grid, which is another common theme. Lastly, LeetCode 766, Toeplitz Matrix, involves validating specific conditions across rows and columns. Studying these problems can provide valuable insights and help you recognize recurring patterns in grid-based challenges. There are multiple approaches to solving lonely pixeli, each with its own trade-offs. One efficient method is to pre-compute row and column counts. This involves using two arrays to store the count of black pixels in each row and column. Once this data is pre-computed, you can iterate through the grid to identify lonely black pixels. This approach has a time complexity of O, n asterisk m, and a space complexity of O, n plus m, where n and m are the grid dimensions. While it uses extra space, the pre-computation significantly reduces runtime. Another approach is to use hash maps to store the positions of black pixels in rows and columns. This allows for faster lookups and avoids unnecessary iterations. The time complexity remains O, n asterisk m, but the space complexity depends on the number of black pixels in the grid, making it memory efficient for sparse grids. Lastly, there's the brute force approach, which checks every pixel in the grid and validates its row and column for loneliness. While simple to implement, it is highly inefficient with a worst-case time complexity of O, n cubed, making it unsuitable for larger grids. Understanding these trade-offs helps you choose the right approach based on the problem constraints. Thank you for joining us in solving lonely pixeli. We explored the brute force approach, discussed its complexity, and identified key takeaways. Keep practicing, and be sure to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!